Hello, my name is Jim Watkins, Director of the National Science Foundation Center for Hierarchical Manufacturing at the University of Massachusetts Amherst. At the center, we think about ways to create cost-effective manufacturing platforms from nanotechnology-enabled devices. These devices have the potential to improve our lives in many ways in fields ranging from healthcare to energy conversion to flexible electronics and displays. In order to create these processes, we use a number of approaches. These include bottom-up approaches such as self-assembly and additive-driven assembly, and high-speed patterning techniques such as nanoimprint lithography. Today I'd like to share with you an example of these approaches through the fabrication of floating gate memory on flexible substrates.
Floating gate memory is a class of computer memory used in data storage. It is based on the field effect transistor, which is the fundamental building block of modern digital logic and computing technology. A field effect transistor consists of three terminals, called the source, the drain, and the gate, that are connected by a semiconducting channel. The most common type of FET, the metal oxide semiconductor FET or MOSFET, also includes an insulator between the gate and the semiconductor. Electric current flows between the source and the drain, while the gate terminal provides a means to control the behavior of the current flow. In the simplest type of FET, the semiconductor creates a large potential barrier, cutting off any source-drain current. Even when a voltage is applied between the source and the drain, very few electrons are able to make it over the potential barrier, and there is very little current. Applying a voltage to the gate terminal creates a conducting pathway in the semiconductor, lowering the potential barrier between the source and the drain and making it easier for current to flow. As the source-drain voltage increases, the current slowly increases with it until it reaches a certain saturation current and levels off. Over the same range of source-drain voltages, raising the gate voltage raises the rate of increase of the drain current in the linear regime, raises the saturation current so that more electrons flow at high voltages, and lowers the saturation voltage, where the curve levels off. Because its transfer characteristics are so highly dependent on the gate voltage, an FET can be used as a binary switch, where it is considered on when it has a gate voltage above a certain threshold, and off when it has a voltage below. This allows FETs to be used as part of logic gates on an integrated circuit, or to store binary code, translating ones and zeros into ons and offs. MOSFET circuits are commonly used in computers for random access memory, or RAM, which holds information the computer is currently using. However, because the gate terminal depends on an external voltage source, MOSFET memory can't be shut off or unplugged without losing its information. This makes it unsuitable for use as non-volatile memory, which stores information the computer won't lose when it is shut down. Traditionally, non-volatile memory is stored magnetically by changing the polarity of regions in a hard disk. Magnetic memory is much slower and less dense than MOSFET memory, making hard drive access speed a major bottleneck in computer performance. MOSFET memory can be adapted for non-volatile data storage by isolating the gate electrode with an extra layer of insulation and adding a control terminal. Applying a large voltage to the control gate will cause electrons to tunnel through the insulator to the floating gate. The charge will remain when the control gate is turned off, allowing the gate to be left open or closed with no external power supply. This modified MOSFET device is called floating gate memory, or FGM. It is commonly referred to as flash memory, and is widely used in mobile devices and in portable thumb drives. Its increasing use in computer hard drives provides significant improvements in memory access speed, greatly improving performance. However, flash memory is considerably more expensive than magnetic memory. Partially this is because, like all microchip-based technology, it is manufactured by batch processing. Microprocessors, random access memory chips, FGM, and similar devices are made by printing millions or billions of MOSFETs in complicated patterns on silicon wafers. The bulk silicon itself forms the semiconducting pathway, while the source and drain terminals are usually made by depositing a metal such as aluminum on the wafer. The insulating layer is generally made by depositing a high-K oxide before depositing the gate terminal. Batch processing is called a top-down manufacturing technique because order is imposed from above, by patterning features photolithographically on the surface of the wafer and filling them in with deposition or etch steps. Each layer of the device requires several such steps involving spin coating, photolithography, sputtering, or any of a large number of other techniques. For complex chips, very many complicated process steps may be involved, and each must be carried out by a piece of dedicated equipment. This need for dedicated processing stations makes batch processing very expensive, requiring a large amount of overhead in space and in equipment. A modern nanofabrication facility can cost over $4 billion and can produce floating gate memory at a cost between about 40 cents and $4 per gigabyte, depending on the cell configuration. Researchers at the Center for Hierarchical Manufacturing are merging top-down and bottom-up processes, developing new materials, and pioneering process techniques that can significantly reduce the cost of FGM and many other technologies. One area of development is roll-to-roll manufacturing, where nanoelectronics, nanomaterials, or functional nanostructures are printed on a flexible polymer ribbon, rather than slowly built on a rigid wafer. Roll-to-roll techniques are most convenient when each layer of the device can be applied in solution and quickly cured. Polymers and nanoparticle polymer composites are ideal, as they can easily be applied by gravure rollers or slot die coating. Roll-to-roll compatible sputtering chambers and atomic layer deposition coaters can be adapted as well, so that thin metal films can also be deposited on the web. Because of roll-to-roll manufacturing's assembly line style production, it offers greatly reduced cost per device at a greatly increased rate of production. Because it does not require several dedicated process stations, it offers massively reduced overhead in space and in equipment. The center is currently developing an FGM device which can be produced by fully roll-to-roll compatible solution-based processing. Where current production techniques produce FGM at a cost of 40 to 400 cents per gigabyte, costs on the order of 4 to 20 cents per gigabyte are expected from roll-to-roll production. The center's manufacturing technique depends on replacing the floating gate layer of the FGM device with a self-assembled dispersion of gold nanoparticles in a polymer dielectric. A semiconducting polymer is used for the channel, and metal films are used for the source and the drain. Without the nanoparticles in the dielectric layer, the device behaves like a typical MOSFET. When the gold nanoparticles are added, they create a memory window in the transfer curves. As the nanoparticle loading increases, the memory window widens. The memory window continues to widen up to a critical density. Because the device characteristics are highly responsive to nanoparticle loading, they can be easily tuned for specific applications. Data storage in the FGM device is completely reversible. By applying an appropriate gate voltage, the device can be fully programmed or erased. Memory characteristics are stable over more than 4,000 write cycles. In order to be compatible with typical digital circuitry and to further improve the efficiency of the FGM device, it is important that the gate switching voltage be around 1 or 2 volts. Traditional insulators such as silicon dioxide or polymer-based dielectrics have low dielectric constants, resulting in large gate switching voltages. A lower gate voltage can be achieved by replacing the dielectric with a high K material such as zirconia dioxide. In order to do this by solution processing, ZrO2 nanoparticles are mixed in a polymer solution. Using innovative chemical techniques, very high nanoparticle loadings are possible. Using these high K gate dielectric films, gate switching voltages have been reduced from about 20 volts to about 1 volt. Beyond floating gate memory, roll-to-roll manufacturing offers much lower costs for many other nanoelectronic and computing components. In many application areas, economy of scale is expected to drive manufacturing costs to as little as $25 per square meter. As one of many innovative technologies being developed at the Center for Hierarchical Manufacturing, roll-to-roll production promises to make expensive and inaccessible technologies more affordable and more available.